So here we have a problem we'd like to work. And the situation is calling for us to estimate the average lung capacity for all U.S. lung cancer patients. For all U.S. lung cancer patients. So we're estimating the population mean here, right? Estimating the average for all lung cancer patients. So we're estimating for all. So we're estimating the population's mean, population's average. Do we know sigma? Do we know the population standard deviation? So some of you are going to read that question. And you're going to say, hey, we got a standard deviation there, right? Standard deviation is 0.8. But hey, if you read that really carefully, that is not sigma. No, we don't have sigma. We don't have the population standard deviation. We have the standard deviation of the sample. So that is S. That is 0.8, right? Read that sentence again. So we have a sample of 25 patients. That's the patients. Their average is 3.9. That's the sample's average. And their standard deviation is 0.8. So that's the sample standard deviation. This is the sample standard deviation. It'd be nice if this actually wrote sample standard deviation, not the population standard deviation. So anytime you hear that you're estimating population mean, and you have the sample standard deviation rather than the population standard deviation, we're going to use a T confidence interval. A T confidence interval. Exciting, right? Let's see if we can remember the formula for a T confidence interval. T confidence interval. So you're trying to estimate the population mean. It's going to be bounded above by what? X bar plus T alpha over 2 times S over the square root of N. And bounded below by X bar minus T alpha over 2 times S over the square root of N. So, you go back and read carefully, really carefully. Looks like we had a sample of size 25, right? We had 25 patients that we sampled from. So N is 25. What else? What was the average of the sample? X bar. 3.9, right? There, that's the sample's average, is 3.9. So here I go. X bar is equal to 3.9. What's S? The standard deviation of the sample. We said it was 0.8, right? And now we got to find T alpha over 2. This is called the critical T value. So there's a little work in finding the critical T value. So to find the critical T value, first of all, you need the area and 2 tails. Area and 2 tails. What color am I going to put that in? I'll do it in the purple. Area. Two tails. So I can get this to work. So we calculated that by taking 1 minus the 95% confidence level, right? You want a 95% confidence level, so 100% minus 95%, 1 minus 0.95. That's going to be 0.05. 0.05. So there's the area in 2 tails, sometimes called alpha. Sometimes that's called alpha. Alpha is 0.05. The second thing you're going to need here is the degrees of freedom. Degrees of freedom, I'll do these in yellow. DF. So to find degrees of freedom, I take my sample size, which we had back here was 25, right? And subtract 1. So we're going to get degrees of freedom are 24. So now I'm going to have to go to my table to find this T alpha over 2 number, this critical number right here. I'm going to go to my T table, look up area in 2 tails is 0.05, degrees of freedom is 24, so let's see if we can find that. So here we go, area in 2 tails is 0.05. That is the third column right in the middle, right? Area in 2 tails is 0.05. We're going to scroll down to degrees of freedom being 24. 24. So I find the number 2.064, right? So again, area in 2 tails, 0.05 is the column we're looking at. 24 is degrees of freedom on the left. And you find the critical number of 2.064 there in the middle. So let's write that, 2.064. So now we have all the information we need to plug into our T confidence interval formula. So first of all, x bar, we're going to have what? 3.9 minus T alpha over 2 is 2.064 multiplied by S. What was it? S? 0.8 divided by the square root of 25. That's going to be less than mu, and that's going to be less than x bar, which is 3.9, plus T alpha over 2, which is 2.064, multiplied by S, which is 0.8, and that's going to be divided by the square root of 25. So what we're going to do, we're going to calculate this dude right here in this cool box. Come on, it's not writing. There it goes. Look at that neat color. It's kind of like a blue, baby blue color. I call the number in the box right there. We're going to calculate that number in the box. We're going to leave the 3.9s alone. Let's scroll a little bit. So I'm going to have a 3.9. Come on, 3.9. You can write. You can write. Minus. Let's calculate that. Baby blue box. 2.064 times 0.8. 2.064 times 0.8 divided by the square root of 25. It's going to give us about 0.33024. That's going to be less than the population mean, mu, and that's going to be less than 3.9. Come on, you can write. You can write. 3.9 plus 0.33024. All right, so I've calculated what's in the little baby blue box. It's 0.33024. We're subtracting it on the left. We're adding it on the right. So now on the left, we're going to take what? 3.9 minus 0.33024. And we get about, let's round it to 3.57. And on the right, let's do 3.9 plus 0.33024. Let's round that to 4.23. There's your confidence interval. So now we want to write a little conclusion. We're going to say we are 95% confident that the average lung capacity for all lung cancer patients in the USA is between 3.57 and 4.23 liters. And that's it.